Hello, good morning, guys. So in the last class, we discussed about trunking, tagging. We discussed about the DTP protocol and VTP protocol. So trunking is the process of forming a trunk. When two switches connected to each other, they negotiate a trunk link with each other. Means they form a trunk link. That is trunking. So trunking can be done either manually or dynamically. So during the manual trunk, you form a permanent trunk using the command switch port mode trunk. Okay. Switch port mode trunk. And during the dynamic trunking format, you use the protocol DTP, that is dynamic trunking protocol. Correct. Then for trunking, when trunk links are created and when any frame is traveling through the trunk link, the frames are being tagged. So for tagging, we use two protocols. One is the ISL and second is the IEEE 802.1Q, or in short, you will just call it as a .1Q. This protocol is being used. When this ISL, this is Cisco proprietary protocol. ISL is Cisco proprietary and it adds 30 bytes of extra information, 26 bytes of header and 4 bytes of trailer. While your IEEE.1Q, the .1Q protocol, it adds only 4 bytes of information. Then in case of your ISL, your native VLAN frames are also tagged. Native VLAN frames are tagged. Means even the frames that are not having any tag, it is going to tag them with the native VLAN information and it is going to put this extra 30 bytes of information. But in case of .1Q, native VLAN frames are not tagged. This is clear. Then we discussed about the VTP protocol. The VTP protocol, VLAN trunking protocol. VTP stands for VLAN trunking protocol. So this VTP protocol is used to synchronize your VLAN database across your network. Let's say in your network, you are having certain switches and you want to synchronize the VLAN database on all the switches. So you will use this protocol VTP. In the VTP, we are having three modes. First is the server mode. Second is the transparent mode. And third is the client mode. By default, all your switches, all your Cisco switches, because both of these protocols, they are Cisco proprietary, means works only in Cisco devices. Okay. So by default, all your switches are in server mode. All your switches are in server mode. And when a switch is in server mode, it can create VLANs, delete VLANs, edit VLANs. Okay. Create, edit, and delete. Along with this, they can also advertise the VLAN. Whatever VLAN database is there, they can advertise this VLAN database to the other switches. When a switch is in client mode, it cannot create, edit, or delete VLANs. Your client will accept the advertisements from the server and update its own VLAN database accordingly. It will just accept the advertisements from the server. And again, if you are having multiple servers, your clients are going to accept the information, the advertisements from the server with the highest revision number. Means the server switch, which has highest revision number, means in which configurations has been revised multiple times, higher number of times. Okay. From that switch, it is going to take the advertisement. Then we have a transparent mode. So in transparent mode, they will not participate. Okay. You can say these switches do not participate in VLAN advertisements. Okay, they will not participate. They are not going to accept the server advertisements and update the VLAN database. They are just going to forward whatever advertisements are coming from the server. They are just going to pass them to the clients, to the next switches. Okay. Now these can also create, or you can simply say, can modify local VLAN database. Means they can create, edit, and delete VLANs in their own database. They are not going to exchange or share this information with any other switches. Is that clear? So this was the part we discussed yesterday. Today we'll be discussing about spanning tree protocol, the STP. Okay. Before going into the STP, let's say you have a switch. This is your switch 1. Now this switch is connected to switch 2. These two switches are connected. Let's say I'm having one host this side, PC1 with IP 10.0.0.1, and I'm having PC2 this side, IP 10.0.0.2. They will communicate with each other. But what will happen if this link goes down? Communication will stop. Means we can call this situation as a single point of failure. Why? Because this is a single point. If it fails, the network fails, the communication fails, right? So what we can do?
The physical media
we have to change it. So means we will always have the single point of failure. To overcome this, we can use redundancy, backup. What we can do, we can connect one more cable. Correct? We can use one more cable. Let's say this was F0/1. This is F0/2 connected to F0/2. And we also connected F0/3 connected to F0/3. So right now, is there a single point of failure? No. Because if this link fails, if the first link F0/2 fails, we still have connectivity through the F0/3. Correct? But there is a problem. What is the problem? Loop. In your network, loop is going to form. How loop is going to form? Understand. If by mistake or due to any reason, let's say, for example, not by mistake, not due to any reason, this PC initially wants to communicate with PC2. They does not know about each other. So what your PC1 is going to do? Generate a ARP. Okay. Generated a ARP. ARP is a broadcast packet. And how a switch deals with the broadcast packet?
it will, broadcast to the all
Broadcast to each and every port other than the port it was received on. Means it will be sent this side as well as this side. Right now, we'll consider one scenario when this was forwarded through the F0/2 only. Okay. So this forwarded again here. Switch 2 received the broadcast packet. How your switch 2 is going to deal with it? Again broadcast this side, then this side. Correct? Then again, your switch 1 received on which port? F0/3. How your switch is going to deal with it? Again broadcast. Right? Means this side as well as this side. And you see, this will keep on looping. This is one scenario when we have considered just F0/2 situation. Because your broadcast message, it will be forwarded through the F0/3 also. The ARP message sent by this, it will send on F0/2 as well as F0/3. So when F0/3 message is coming this side, how your switch is going to deal with it? Broadcast this side as well as this side. And again, it received on F0/2, and this will be again broadcast. So means in your network, there will be total 2 loops working. One will be in this direction, and the second loop will be in the opposite direction, clockwise as well as anti-clockwise. And right now, I have considered just one system. What if the switches are connected like just 2 switches I have considered? Let's say the switches are connected like this in the stack. So each and every switch has been provided redundancy. Like this. You can imagine the amount of traffic that will be there in your network. Because this kind of setup is being used in the networks. This kind of setup is being used in the networks. When we'll study about architectures, network architectures. Okay. So let's say this is switch 1, this is switch 2, this is switch 3, this is switch 4. So you can see how many redundant links are there. And if there is a broadcast, there will be actually a broadcast storm in your network. This will create a situation that is broadcast storm. Now, how to avoid this? Because you see, we tried to provide a redundancy, but instead of redundancy, we did something else. Because this is going to bring your network down. Because again, you see, every time the packet doubles. If you see, every time one packet is received and 2 packets are generated. And if there are multiple links, multiple redundant links, then the amount of traffic will be there. The broadcast traffic in your network that will be used. And your switches will just be busy opening those broadcast packets, checking the destination MAC address and forwarding them. And ultimately, the CPU will be overused and your network or switches will come down. Is that clear? To avoid this problem, we have a protocol. Okay, to avoid this situation, we have a protocol that is your spanning tree protocol. That is your spanning tree protocol. How your spanning tree is, what your spanning tree is going to do, whenever it sees there is a possible loop in the network. If you are connecting the links, and first of all, let's say you connected these two switches with two links. So before these ports come up, before any data transfer starts, your STP protocol is going to work, and it is going to check, is there a possibility of loop? And if it finds, okay, there is a possibility of loop, instantly it is going to block one of the link. It is instantly going to block one of the link, means this link will be now useless. Through this link, you cannot transfer the data. Okay. So ultimately, you will have only one link. Ultimately, you will have only one link. So if you have only one link, then there is no chance of loop, because the data packets, they will not be coming back. The frames, they'll not be coming back to the same switch, because this will be a situation something like this one. So will it form any loop? No. Is it clear how your STP is going to work? STP is going to block a port or a link, and with the blocked link, you will not have any communication. So there will be no loop. Means whatever money you wasted for that cable, that is waste. So how it is going to work, how the redundancy is going to work, if anyhow the F0/2 goes down, in that case, your second port will come automatically up and you will have the connectivity. Is that clear? Yes. Online people?
Yes, sir.
Okay.
So how many ports can a switch could have?
24 ports.
No, not that. The interfaces.
Yeah, interface is 24.
24. So every port could be considered as interface.
Yeah, every port is an interface. Okay. Is that clear? Port and interface, same thing.
No.
Okay. Is that clear? Port and interface is the same thing. Just the name. Okay. But port sometimes you can consider as a physical opening also. And interface can be logical also, like your loopback interfaces. Okay. All right. So we'll consider a scenario. For redundancy purpose, I'll use two links. Let's consider this is F0/1 and this one is F0/2. The next link will be F0/3 and F0/4. This is correct? Yes. This might be confusing you. Let's keep them separate. This is your switch 1, switch 2, and switch 3. Yes. Either, see, it is going to work even if you have one redundant link. Means single link, that is not there, it is not going to work because only one link, no chance of it. But still on the one link also, it is going to check whether it is forming the loop. Okay. But when you are having more than one link, means two links, one is main link and second is the redundant link. In that case, it is always going to block one link. Okay. And if you have more than two, then it is just going to keep one and block the rest of them.
If the main loop falls, then it will automatically open the second.
Yes. We'll see that how your STP works. So let's say this is F0/1, F0/2, F0/3, and F0/4. This side again, F0/1, F0/2, F0/3, F0/4. This will be F0/3, and this will be F0/1. Okay, this is the scenario. Okay, let's consider MAC address of switch 1 is A. MAC address of switch 2 is B, and MAC address of switch 3 is okay. Now, how your STP is going to work? So first of all, initially when your STP sees, okay, two redundant links means need to block one. Okay, so it is going to, let's say, block this link. Okay, again, two redundant link means let's say it is going to block this one. And here also it is going to block. 3 links are blocked. Okay. But now again, let's consider if there is a broadcast on switch 1. Switch 1 is going to broadcast it this side as well as this side. Received by switch 2, broadcast this side. Correct. Received by switch 3, broadcast this side. Again, this side as well as this side. Still there is a loop. Still there is a loop. So what your switch is, STP is going to do, it is going to block, let's say again, this link. Now, if this link is also blocked, this traffic will not pass this side. Correct. Means it will not go back. And from switch 1, the connectivity is coming to switch 2 as well as switch 3. So your entire network is going to have the connectivity, but there will be no loop. So how many links blocked? 4 links. But how does your STP makes a decision how to block the links? Okay, how to block the link. Okay, or even you can make it more simple. This might confuse you because there are a lot of cables already. So just consider 3 switches with one link. This will be more easy to understand. So if your switch 1 gets a broadcast, what will happen? Forward this side as well as this side. Then switch 2 is going to forward this side and switch 3 is going to forward back. Similarly, if switch 3 received, it is going to forward this side as well as it is going to forward this side. 2 loops are there. So if your STP blocks this link, these are not going to travel like this. Correct. So you will have the connectivity. No issues. Correct. Any doubt in this part? Okay. Now, how your STP makes your blocking decisions, that we'll understand. Okay. So for understanding that, I'll use this scenario because right now this is going to confuse you because two links. Okay. So let me directly go to packet tracer. This is all A, this one is all B, and the third switch is all C. Now, as soon as these switches are connected with each other, they are going to send a special type of message that is known as BPDU. They are going to send a message that is known as BPDU. BPDU stands for Bridge Protocol Data Unit. They are going to send this message. In this particular message, they are going to send some information to all the switches. Means each and every switch is going to send, switch 2 is going to send this side, switch 1 is going to send this side, and switch 3 is going to send this side as well as this side. They will exchange these messages. Okay. In these messages, they will send the bridge ID information. They are going to send bridge ID information. So what is this bridge ID information? This is going to include priority plus MAC address information. This is going to include priority plus MAC address information. So how your switches make a blocking decision that which ports it needs to be blocked. So first thing it is going to do, it is going to select or elect, you can say, a reference point. And that reference point, you call it as a root bridge. It is going to select, like in your OSPF, we have DR-BDR concept. Okay. Here we have the root bridge. So all the 3 switches, they are going to communicate with each other and they are going to elect a root bridge. Now, who will be the root bridge? So first thing that is checked is the least priority. First thing that is checked is the least priority. And second thing, if priority is equal, least MAC address. If priority is same, then it is going to check least MAC address. Okay. Now, by default, the priority will be 32768. This is the priority value by default for all the switches. Means this switch is also having the priority 32768. Switch 2 is also having the same priority. Switch 3 is also having the same priority. So means looking at the priority, we cannot decide what will be the or who will be the root bridge. But then we are going to check least MAC address. So which switch is having the least MAC address? Switch 1, A. So this will become your root bridge. Now this is the reference point. With this reference point, the next step will come into picture and they will elect root ports. Now what are these root ports? See, this is the root bridge. Switch 1 is the root bridge. So remaining 2 switches, they will be called as non-root bridge. means they are not the root bridge. And this is also non-root bridge. Now these non-root bridge switches, they are going to calculate the shortest path towards the root bridge. Okay, so let me give them the interface names. Let's say F0 by 1, F0 by 2, F0 by 1, F0 by 2, F0 by 1, and F0 by 2. Okay, so according to switch 2, which port or which link have the shortest path towards the root bridge? According to switch 2, which port or which path has the shortest path towards the root bridge? According to switch 2, F0 by 1 has the shortest path towards the root bridge, right? Let me remove this. So this particular port, this will be your root port. Okay. For switch 3, F0 by 2. So this will be the root port. Okay. So about root ports, what are the root ports? First of all, these are elected on non-root bridges. Only non-root bridge switches are going to have these ports. Second thing, these are the shortest coast towards the root bridge. These are the shortest coast. Now, what is this coast? So for each and every link is having some bandwidth. According to that bandwidth, some default coast has been defined. Okay, like your 100 Mbps link having the coast 19, your 1 Gbps link having the coast 4. Okay, so if these are 100 Mbps link, this will be the 19. Again, this will be the 19, and this will be the 19. So if your switch 2 tries to come this way, what will be the total cost? 19 plus 19, 38. And if your switch 2 is coming directly, this is 19. So it will see, okay, this is the least cost. So this is my shortest path to the root bridge. And this port will be elected as your root port. This is clear. Similarly, your switch 3 is going to select, and it is going to see if I go this way, this will be 38. And if I go directly through the F0 by 2, this will be 19. So shortest cost or the least cost towards the root bridge, that will be your root port. This is clear. Next election will be designated ports. Next election will be designated ports. So the ports that are directly connected, to the root port, they will be your designated port. So according to this, which ports will be the designated port? F0 by 1 and F0 by 2. Means this will be your designated port.
0 by 2 and already connected to switch 2. 0 2. You need to say switch 3.
Oh, okay. Understood. This is also, this is F0 by 2 and this is F0 by 1. Now, okay. Okay. So this will be designated port as well as this port will be designated port. Now about designated ports, first thing, each and every link will have a designated port. Means it can be available on root bridge as well as non-root bridge. Okay. Can be available on root bridge and non-root bridge. I'll say non-RP. This is clear. So it can be present on root bridge as well as non-root bridge switches. So these two links, this link is already having a designated port. This link is already having a designated port. This link is not having a designated port. Now, which port to select? Which port to select as a designated port? So they are going to make a decision. Again, there will be some comparison. So whenever you want to calculate the last, you want to calculate the designated ports, they will check first of all cost. Again, if you go through this port, this is the same cost, 938. And if you go like this also, this is the same cost, 38. So cost doesn't work. Next, we are going to check the bridge ID. So in the bridge ID, first of all, we'll check the priority. So priority again, same, type. Then we'll go for the MAC address. Now, according to switch 2 and switch 3, which switch is having the least MAC address? Switch 2 means the port of switch 2 that will be selected as the designated port.
But in the real scenario, the MAC address is completely different, right?
Yes.
How it will identify.
I'll show you the comparison. Okay, this is clear. This port will become the designated port. Now, all the ports other than root port and designated port, those all ports will be the blocking ports. Means those are the ports that will be blocked. So according to this scenario, this is the port that will be blocked. So this will be the blocking port, or you can say alternating port. So this is how your STP makes blocking decision, that which port to block. First step, it is going to elect root bridge. Root bridge election is going to happen on the basis of least priority. And if priority is a tie, least MAC address. Okay. Then second step, it is going to select root ports. So root ports is what? The shortest path towards your root bridge. So all your non-root bridge switches, they are going to select the shortest path towards your root bridge. And those particular ports will be root ports. Next step is the designated port. So first thing, the designated ports can be available on root bridge as well as non-root bridge. Means each and every link in your topology is going to have a designated port. This is clear. Now, how to identify the designated ports? So first, what you're going to do, the ports that are directly connected to your root ports, they will be your designated ports. Selected already. So in short, you can say all the ports of your root bridge will be designated ports. All the ports of your root bridge, they will be designated ports. This is clear. Okay. Now designated port selected. But again, there will be a situation when the port is not on the root bridge. The scenario like between switch 2 and switch 3. These ports are not available on root bridge, right? These are non-root bridge switches. Now we have to select designated port. So how we are going to select? First of all, they are going to check the cost. The cost will be generally equal. So next we are going to go for the bridge ID. In the bridge ID again, first priority will be checked. If priority is same, then MAC address will be checked. And MAC address will obviously be different. MAC address will obviously be different. So whichever switch is having the least MAC address, that will become that port will become the designated ports. And all the ports other than your designated ports and root ports, they will be the blocking ports. Is that clear? This is clear?
The least MAC address would be designated.
Yes.
What if the faraway router switch has at least MAC address?
Far away means?
I mean, say for example, it's
Again, a link will have only two connections, two ends. So either of them is going to have only two MAC addresses, and either of them is going to have the least one, and that will be the designated port. It can be either your switch 3 or can be your switch 2. Okay. So if there is again a switch connected like this, so there will be new election here. It will not be considered from this one. Okay. Now from, let's say this switch is having D, then this will be the designated and this will be the blocking, like this. Is that clear? Any doubt? There is clear how your STP is going to work. See, in STP, we are not having any type of configuration. This is by default running in your switches. Okay. This is by default running in your switches. We just need to understand the concept. Now, what kind of configuration you can do in your STP is you can manipulate this root bridge election. You can decide which switch is going to be the root bridge. Okay. You can change the priority. You can change the priority. If you, let's say it's right now switch 1 is having the least MAC address. But if you change the priority of this switch and you bring it, let's say less than 32768. If this priority is less than 32768, then what will happen? This will become the root bridge. Okay. This is clear.
what is the range of number that we could provide? What is the range of number?
Range of numbers?
For that ID?
Bridge ID?
32768.
This is again by default selected. And it is in the multiple of 4096. Okay. And 65,536. Okay. This is clear. Okay. It is in the multiple of 4096. Okay.
So according to that, we can change the priority number.
Yes, you can change. But again, this configuration part is not in here CCNA. It will be there in your CCNP. Okay. Because these protocols, whatever we are studying here, we are studying the introduction, details, will be there in your CCNP enterprise. You will be having certain different, let's say module, CCNP switching, CCNP routing. So there you will be studying all these protocols. Is that clear? But right now you understand how your STP works and how it blocks the ports. Okay. So one more thing you can note down from here is your root port and your designated ports. They will always be forwarding. Forwarding means they will always be in forwarding condition. They will be always on. They will not be blocked. These ports will not be blocked. Okay. And your blocking port or alternating port, that one will be the blocked. Is that clear? Then these ports, before going to the forwarding condition, they pass through certain, you can say, states. Before going to the forwarding condition, they pass through certain states. What are the states? First is the down. Second is the blocking. Third is the listening. Fourth is the learning. And fifth is the forwarding. These are the 5 states. Your ports, they pass through these 5 states before coming into the forwarding state. So down means the port is down. You have given the shutdown command or you have not connected any cable to that port. In that case, the port is down. This is the first state. Whenever you connect the cable, you are not able to transfer data instantly. That port will remain some time in the blocking state. And how long it is going to stay? It is going to stay for 20 seconds. For 20 seconds, it is going to stay in the blocking state. Then after, it will start listening to the BPDUs, listening to the advertisements from the other switches. And here it is going to stay for 15 seconds. Then the learning state. In the learning state, they are going to see who is the root bridge and what are the MAC addresses. So they will learn the MAC address about the other switches and devices. In this state, it will remain for 15 seconds. And finally, the forwarding, when they will start forwarding the data. So total, how much time it will take for the port to come up? 50 seconds. Means you connect a cable in the switch and for 50 seconds, you are not able to transfer any data. You're not able to transfer any data or any type of communication you will not be able to have. Is that clear? Okay. Now we'll see the presentation. This is clear, right? So first of all, what is STP? So STP is a switching protocol that prevents layer 2 loops. It is going to prevent your layer 2 loops created by the redundant links. STP enables switches to become well informed of each other so they can negotiate a loop-free path through the network. Means those switches are going to communicate with each other and they are going to find a loop-free path. Means it should not create a loop. Now, how STP works? So STP chooses one of the switches as a root bridge. First of all, it will choose as a root bridge, which will be used as a reference point, because looking at the your root bridge only, we decide which are the root ports, which are the designated ports. All the calculation happens based keeping that root bridge in mind, reference. Then calculate all redundant paths to the root bridge, picks one path which is the best to forward the frames, and blocks other redundant paths. Okay. Due to this redundant path blocking happens, switching loops are prevented. Okay. By blocking the ports, it is going to prevent loops. Now it is going to send the special type of message, that is your BPDU. So all the switches switch over information to select the root bridge and for configuration of the network. This is done through the messages called bridge protocol data unit. Each switch compare the parameters in the BPDU message that it sent to one neighbor switch with the one that it received from another neighbor switch. Means whichever BPDUs they are receiving, they are going to compare the bridge ID and priority, and they are going to decide, okay, who has the least MAC address or who is the least priority, and that particular switch will become the root bridge. Okay. So there are 2 types of BPDUs. One is the configuration BPDU. These are the messages we use in the STP, and one is the TCN BPDU. This again CCNP concept. Okay. So this TCN, it is used to advertise the changes in the topology. TCN stands for topology change notification. Okay. So this configuration BPDU is used for STP assessment. For STP, we just require this one. What is the bridge ID? We say they are going to compare the bridge ID. So bridge ID is 8 bytes long. It includes both priority and MAC address of the device. In the STP domain, bridge ID is used to select the root bridge. How root bridge is elected? So see, in STP domain, the bridge with the lowest bridge ID is elected as the root bridge. This means the switch with the lowest priority will be elected as the root bridge. And if two or more switches have the same priority, the switch with the lowest MAC address will be elected as the root bridge. This is clear. And this is how your STP works. So first of all, the root bridge is elected. So who is the root bridge? The one with the least MAC address or least priority. Then after, calculate path cost and root path cost every bridge. This is optional. Means if you are having multiple switches, then again, who will be the root bridge? And when you are selecting the root bridge, again, root bridge also you can do for primary and secondary. If your primary root bridge goes down, your secondary root bridge will start forwarding the receipt, start becoming the root bridge. Because by default, your priority is 32768. Right? So if you are having two switches, let's say this is the scenario, because your entire traffic will be passing through the root bridge. And if you see, this is the scenario in this case. So let's say this is connected to the router and this side your host are connected, right? So if this is your root bridge, let's say this you create as the root bridge. So what is going to happen? All your traffic will forward like this. But if let's say your root bridge goes down and this switch has the least MAC address, then your traffic will go like this.
It's dynamic.
Hmm?
If
your root bridge goes down, there will be a new election, obviously. Because yes, your switches will be continuously sending the BPDU messages continuously. Okay. And they will be continuously seeing, okay, root bridge is up or down. And as soon as root bridge is down, new root bridge election will be there.
How frequent is this message sent?
Either 2 seconds or 3 seconds. Then once the root bridge is elected, it is going to assign the root ports on the non-root bridge switches. Once the root ports have been elected, next step is the designated ports. The ports in front of your root ports. And after that, assign the non-designated. These non-designated means simply you can say blocking ports. Because we have selected the root port, we have selected the designated ports, the remaining ports will be blocking ports. Then what are these root port designated ports? So the root port is always on the non-root bridges. It is always the port on the link directly connected to the root bridge, or the port on the link which is the shortest path to the root bridge. It is always in the forward state. Forward means it will always forward data. It will not be blocked. Then we have the designated port. It can be on both root bridge as well as non-root bridge. Also, all ports of your root bridge are designated ports. A designated port is the one that has the best cost to the root bridge. Again, they are going to calculate. It will be marked as a forwarding port. Means again, it will also never be blocked. Then what is a forwarding port? A forwarding port can send and receive frames. The port that can send and receive data, that is the forwarding port. And what is the block port? A block port is the port that is used to avoid the switching loops. Okay. It is called non-designated port. It only listens to the BPDU. Means if a port is blocked, through that port, your switch will only listen to the BPDUs. It is not going to send either. Okay. Any port other than root port and designated port is a blocked port. And these are the timers. There are 3 different timers in your STP. Okay. One is the hello timer, forward delay timer, and maximum age timer. What is hello timer? The BPDU messages every 2 seconds. Okay. What is forward delay timer? This forward delay timer tells how long your switch will stay in the listening state and the learning state. And by default, the forward delay timer is 15 seconds. Means in the listening 15 seconds, in the learning 15 seconds. Okay. What is this max age timer? So if a switch doesn't receive a BPDU for a long time from the neighboring switch or from the root bridge, they are going to think that, okay, that is down and new election will happen. Okay. So the hello timer, the time interval between the configuration BPDU messages. This is the interval, and the default value is 2 seconds. Then we have the forward delay timer. So this is the time interval that a switch port spends in both the listening and learning state before going to the forwarding state. And what is the default value? 15 seconds. Max age timer, the maximum length of a time BPDU information can be stored before discarding it. Okay. It can also be defined as the time interval that a switch store BPDU information without receiving an update. And by default, it is 20 seconds. Okay. All these configuration and timers I'll show you. Don't worry.
Just one more down.
Yes.
So like, OSPF, there is an election happens, right? Like that
Yes.
only can happen. here.
Mhm.
What if, that is down and after sometimes it come back up?
Mhm.
So will it be the
Again,
same?
election,
Again?
because it is going to send the BPDUs.
Okay.
So if it
So
is
already, these other switch is already considered as grid switch,
or
right?
see, other switch already have their own root bridge, but as soon as your new switch is coming up,
No,
it is going to send the BPDU message.
not the new switch. Say for example, if a switch is already become a grid switch,
Okay.
okay, so it got down.
Yeah, because it was having high priority, right?
Huh.
Or least MAC address, whatever.
It's not.
But again, if it is coming up, it is going to send the BPDU information.
Then again the election.
Again the election will happen.
Oh. So
Okay.
that particular will become again.
Again the root bridge, because they
Hello.
see. Yes, please.
So designated maybe root port, like
Can you repeat the question?
designated port, maybe root port. You can say that.
No. Designated ports and root ports are different. Root ports, they will always only be available in your non-root bridges, and designated ports, they can be on the root bridge as well as non-root bridge. Okay, is that clear? Then we have the certain STP states. So the first state is disabled. A disabled state does not take part in the STP. Why? Because the port is down. Second is the blocking state. So blocking state will be seen here, this one. So a port in the blocking state does not forward frames. Okay. It only listens to the BPDU message. The function of blocking port is to prevent the use of loop path. Then we have the listening state. What is the listening state? A port in the listening state send and listen BPDUs. They are going to send BPDUs and listen to the BPDUs to make sure no loop occurs on the switch network. The port also arranged to forward data frames without populating MAC address table. Means they are forwarding the BPDU message and frames, right? But they are not making an entry in the MAC address table. They will just check, okay, who is the last priority, who has the last MAC address. Then the learning state. So in the learning state, they are going to learn, okay, this is the least MAC address. Now we have to elect the root bridge. So a port in the learning state populate the MAC address table. They will make entries in the MAC address table, but does not forward data frames. They are not going to forward data frames. The port still send and receive BPDU message as in the listening state. So simply you can say in the disabled, no data, no MAC. Again in the blocking, and also no BPDUs. In the blocking, BPDUs will be sent, but no data, no MAC. In the listening, they will send BPDU, again no data, no MAC. In the learning, they'll start learning the MAC address. So BPDUs will be sent, MAC address will be captured, but no data transmission will happen. And when it is forwarding, in that case, BPDUs will be sent, MAC address table is created, and the data is also forwarded. Okay. So in the learning state, BPDUs will be sent and the MAC address table will be populated, but data transmission will not happen. Your switch will not forward the frames. Still, your switch cannot forward the frames. And in the final state, that is your forwarding state. In the forwarding state, if you see, the port in the forwarding state can send and receive data frames, collect MAC address state, and send and receive BPDU messages, everything. This port is now fully functioning switch port within the spanning tree topology. Is that clear? Okay. Now, what is a root port? After the root bridge is elected, every other switch, means the non-root bridge switches in the STP domain, must elect its single port to reach the root bridge. How it can reach the root bridge? The port with the least root path cost will assigned as the root port. It will always be in the forwarding state. Only non-root bridge switches have a root port, and root bridge will never have a root port, because all the ports of your root bridge, they are the designated ports. Okay. And
the data always travel in the root port.
Root bridge only.
Sorry, root bridge.
Now, what is the path or link or STP path cost value? Okay, so there are certain values. Lesser the bandwidth, higher the cost. Higher the bandwidth, lesser the cost. So for 4 Mbps link, it is 250. So right now we are generally using either 100 Mbps or 1 Gbps. So you just need to remember these two. 100 Mbps 19, 1 Gbps 4 to compare the cost. Okay. Then we have something called as BPDU guard and BPDU filter. And before BPDU guard and BPDU filter, you must need to understand a small concept about port fast. What is port fast? So what happens? Let's say you have the switch. Sorry. This is your switch. And you connect a PC on your switch. Is there any chance of forming a loop? No. But still your STP is going to keep this port for 50 seconds. Means you for 60 seconds, for 50 seconds, you still cannot forward data. Even we know there is no chance of forming a loop, right? There's no chance of forming a loop and still it is going to keep it down for 50 seconds. Means it is going to send the BPDs also. It is going to keep it in listening, learning states also. Blocking, listening and learning states also. So is this a good thing? No. Because every time you connect a system for 50 seconds, you cannot do anything. Okay. So in that case, what we can do, we have a feature and that feature is known as port fast. So what this port fast feature does, it disables STP on this particular port. Okay. Means it will instantly, with the name you can see, port fast means instantly bring the port into forwarding state. Whenever the port fast feature is enabled on a particular port, that port will directly transit into the forwarding state. It will not go through the blocking, listening and learning state. Instantly forwarding state. So as soon as you connect the PC, this will come into the forwarding state. But again, this can create an issue. Let's say you have enabled port fast on this feature. I mean, on this port, you have enabled port fast and there is a system connected. But in your company, there is a smart guy, right? What he's doing? He wants to use his own laptop also. So he connected a switch and he's using his laptop or PC, right? Now, what is going to happen? Let's say what if this switch is having the least MAC address? What if this switch is having the least MAC address? This will become the root bridge and your entire topology of STP will change. Your entire traffic will change, right? So what you can do to prevent this thing, you can use a BPDU guard. You can use BPDU guard. So what is BPDU guard? Again, a configuration, a concept only. So you can, on the port fast interface, you can enable the BPDU guard. So what your BPDU guard does, it checks, or you can say it monitors incoming BPDUs. So whenever this switch will send a BPDU and you have enabled the BPDU guard, your STP will instantly block this port. Your STP will instantly block out this port. And this switch will not have any communication. As soon as on the port fast interface, you have enabled the BPDU guard, and on that port, if your switch receive any BPDU, it will block that port. Okay. So means this guy will not have any communication. In his legit system, neither is legit system, nor is on laptop or PC. This is what BPDU guard is. But again, there is a security issue because your switch is continuously going to send the BPD. So means this guy can take the information. Who is your root bridge? What is the MAC address of your root bridge? These kind of information he can get. What is the bridge ID value? What is the priority value? Right? This information, this particular person can get. So to prevent this, we have another feature. Instead of BPDU guard, we can use BPDU filter. This BPDU filter is going to filter both incoming as well as outgoing BPDU. It will filter incoming and outgoing. This is the first thing. So in case of BPDU guard, if it receives a BPDU, it is going to block the port. Okay. But what your BPDU filter is going to do, it is going to block the port as well as it is going to remove this port fast feature also. It is going to remove this port fast. So the port will instantly not come up. This is clear about BPDU filter and BPDU guard. BPDU guard will filter only incoming BPDUs and BPDU filter will filter both incoming as well as outgoing. Is that clear? Okay.
Then why do we use port fast?
For the clients, if we are using client systems, then we'll not wait for 50 seconds because every time your switch comes up, it is going to take, first of all, it is going to take the booting time of switch, then 50 seconds for STP, right?
In special case only will apply BPDU filter and guard.
On all the port fast interfaces, we'll apply BPDU guard and BPDU filter. Every port fast interface, you will set up port fast for all your clients. and then you'll apply your BPDU filter or BPDU guard.
So you mean to say that this BPDU guard and BPDU filter will only activate when another switch are connected to the.
Yes.
If the client is connected, they will not.
Then they will not be. Clients will not send BPDU because they are not the switches.
Yes.
They will not send the BPDUs, right? BPDUs will only be sent by the switches. Okay. All right. So about BPDU guard, once BPDU guard is enabled, it will keep an eye open for any BPDU entering the access ports. Our main aim is to have a predictable topology and not allow other switches outside our control onto our network. So if a ROG switch is introduced into our topology, it will in most cases transmit a BPDU, right? If the ROG switch has a better values than the existing root bridge, it will cause a topology change in the switching network. Any topology change is a bad news for the user. By configuring the BPDU guard feature on the access port enables the spanning tree protocol to shut down the port in the event that it receives a BPDU packet. This is clear. Then BPDU filter. The BPDU filter, on the other hand, just filters the BPDU on both the directions, incoming as well as outgoing, which effectively disable the STP on the port. Means no STP. BPDU filter will prevent inbound and outbound BPDU. Both side BPDUs it will prevent. So if it will disable the STP, means no root bridge election. So if someone is connecting, there will be no root bridge. But will remove the port fast state on the port if a BPDU is received. Okay, it will remove the port fast feature. So you will have to go and configure it again. Is that clear?
So BPDU.
Yes, please.
Any topology changes is bad news for the user. I
Mhm.
didn't get that one.
See what happens exactly, that let's say right now you're not having the clear idea, but if your switching network is like this, okay. So initially, according to our configuration, let's say we have created this one as the root bridge and this is connected to the router. And this side we are having the system. So if this is the root bridge, all your traffic is going to pass like this. Correct? But in case, let's say I introduced one more switch on this side, and that is having the values lesser than all of them. So this will become the root bridge. Now your traffic will pass like this. Means there will be delay. Okay. So this is the topology change. Because if this will become the root bridge, all the root port, designated port, all those calculations will happen according to this switch. Okay. And if they will happen, the blocking ports will change. And this will completely change your topology. Is that clear?
So it will automatically change.
Yes, automatically it will change because STP is automatic.
Okay, got it.
Okay.
Okay, so when we apply the BPDU filter, the switch still can, access, but the BPDU messages. will be
Yes,
monitored.
incoming and outgoing, no BPDU messages.
Okay,
And port fast feature will be disabled.
disabled for that. So
Yes.
still a client can connect to that
Connect.
switch.
Yeah, that is why it is just filtering the incoming and outgoing. But in case of BPDU guard, it will block that port. So in this case, it will not have the communication, but in this case, it is going to have the communication. Is this clear? Now we are having certain protocols, STP protocols. So you can divide them into two categories. One is the open standard, means working on all the vendors. And second is, Cisco proprietary. So open standard have STP, RSTP, and MSTP. And your Cisco has PVST and RPVST. STP stands for spanning tree protocol. RSTP is rapid spanning tree. MSTP is multiple spanning tree. Okay. PVST, per VLAN spanning tree. And RPVST means rapid PVST, rapid per VLAN spanning tree. So what is the difference? See, when we are talking about STP, so STP is the spanning tree protocol. This is the common spanning tree. Okay. So this is the one that is taking the 50 seconds. But every time we'll not go with the 50 seconds, right? So they came up with the RSTP, rapid STP. And here it takes only few seconds to come up. But again, in case of STP and RSTP, there is only one root bridge for all the VLANs. One root bridge for all the VLANs. Means if you are having multiple VLANs and your network is bigger, and if you have only one root bridge, your entire data will pass through that one switch. And you can imagine that traffic on that switch, and this will create a delay again, right? So for that purpose, they came up with the MSTP. So in MSTP means multiple spanning tree. So for a group of VLANs, you will create one STP. Then for some other group of VLANs, you will create second STP. Means you will have multiple root bridges. But your Cisco, it started working on per VLAN system from the beginning. So your Cisco PVST, it is similar to STP only, taking 50 seconds. But what is the benefit? The benefit is it is already having per VLAN. Means for each and every VLAN, there will be a separate root bridge. Means it will calculate a root bridge for each and every VLAN. And then it was taking 50 seconds. So they came up with also RPVST, rapid PVST. And it again came to the few seconds. Means STP and PVST similar, RSTP and RPVST similar. And MSTP, it is open standard. You can use in Cisco also. Is that clear? Yes or no?
Yeah.
These protocols are clear. So you can see your STP and RSTP, these are open standard. And PVST plus and RPVST plus, these are Cisco standard. Okay. Then convergence of STP and PVST is slow because 50 seconds, and these are fast. And in case of STP and RSTP, you have only one spanning tree, means one root bridge. But in case of PVST and RPVST, one for every VLAN. Is that clear? For each and every VLAN, root bridge calculation will be there. Let's say these are two switches. For example, you have VLAN 10, you have VLAN 20, you have VLAN 10, you have VLAN 20. Now again, by default VLAN is 1. So there will be calculation for three VLANs, VLAN 1, 10 and 20. But due to the default configuration, only one switch will be the root bridge for all three VLANs. And when we have single root bridge for all the VLANs, that is known as CST, common spanning tree. Okay, why? Because the spanning tree is common. We are having calculation for each and every VLAN, but still the spanning tree is 1. Because between these two switches, either of them will have either least priority or least MAC address. But again, we can change the spanning tree also. You can change the root bridge also, that who will be the root bridge. Maybe this is having the least MAC address, but you can change the priority here. Then this will become the root bridge for VLAN 2 or VLAN 20. Okay. Now we'll see this thing. And you'll see right now they are in blocking, listening and learning state. They are going through all those states. So it will take some time to become green, to come to the forwarding state. And you'll see either of them, one port will be in the down state, blocking state. Means one will be orange and remaining all will be green. Correct? Okay. Now looking at this, how to identify who is the root bridge? Just looking at the switches. Let me give the numbers. For example, this is switch 1, this is switch 2, this is switch 3. Switch 2. Why? Because we know that if this is the root bridge, switch 1 and switch 3 are going to calculate the root ports, and root ports are in forwarding state. So this is the sortage path for switch 1 and this is the sortage path for switch 3. So these are the root ports. In front of the root ports, we have designated ports. So means according to our scenario, these should be the root ports. If this is the root bridge, these should be the root ports. And these are the designated ports. And on this link, this one is the designated and this one is the blocking, or you can say alternating. This is clear. So according to this, root bridge is switch 2. But how do we check that who is the root bridge? Okay, so let's go and check. Let's say I'll go to the switch 1 and check. So on the switch 1, you'll go CLI, enable, and you just give the command show spanning tree. That's it. So here, first of all, for which VLAN it is calculating? VLAN 1. Okay. Now you'll see two things. One is the root ID and second is the bridge ID. In the root ID portion, you will find information about root bridge. And this is the self information. Okay. Okay. What is the priority of root bridge? 32769. And now you'll say, I said 32768. So this priority calculated here is your priority plus VLAN ID. What is the VLAN right now? 1. So 32768 plus 1, 32769. Okay. Then this is the MAC address of your root bridge. This is the cost, how much cost it is there to reach the root bridge, 19. because fast Ethernet. Then the port information. On this port, your root bridge is connected. So if you see, right now we are on the switch 1, and it is saying on fast Ethernet 0/1, the root bridge is connected. Check. Fast Ethernet 0/1, the root bridge is connected, right? Okay. Then this is your hello timer, 2 seconds. Max is 20 seconds. And this is the forward delay, 15 seconds. All information is there. Then again, this is the self information. This is the priority, means priority plus your VLAN ID. This is the MAC address. Again, the timers. And this is the aging time, because again, max aging time. This is clear. Now you see 2 interfaces are there on the switch. And F0/1 is the root port. F0/2 is the designated ports on the switch 1. Let's check. So according to this scenario, F0/1 is the root port and F0/2 is the designated port. Then what is the state of the port? Forwarding. This is the coast and this is point-to-point link. Okay. Is that clear? Okay. Now check on the root bridge. All the ports of the root bridge are designated ports. So you'll say show spanning tree. Root bridge information, self information. Oh, in the last part, one more thing left. The comparison of the MAC addresses. You want to compare, right? So if you compare 0001, similar, 6469. So just 6 and 9, which is the bigger? Self is the bigger, means this is the lower. So this will be the root bridge. Because root bridge is elected with the least MAC address or least priority. So priority by default same. But MAC address is smaller. This is clear. If you check on the root bridge. So first of all, 2 ports are there. All ports of your root bridge are designated ports and in the forwarding condition. This is the root bridge information. This is the self information. You can see some MAC addresses. And here it is going to say you, this bridge is the root. Means this is the switch, that is the root bridge. Okay. This is clear. Check on the switch 3. Enable show spanning tree. So again, same thing, root bridge information, self information. So if you check, one port is the blocking port, F0/1. And compare the MAC addresses, 6469, 5C. First compare 0001, 60, already greater. So this is clear about the STP.
19 is in terms of
Fast Ethernet.
let's say 19 is in terms of currency or
No, just post. No unit. Yes. This is no unit, just a number. Is that clear? There is no unit. It's just like in your OSPF also you'll see cost metric. Again, they are not having the units. Okay. This is clear? Yes.
Please go to the topology. Here, right now, F0 on switch 3 is already blocked. But as per the this scenario, it should only get blocked if the traffic is, like high or something.
Forming the loop, you mean? So it will form the loop. If there is a traffic, let's say any broadcast on switch 1, it will forward this side, this side. So if it is not blocked, this switch is going to forward this side. Again, this switch is going to forward this side. There will be a loop this side.
Okay, that doesn't mean we have to give the ping. That doesn't mean that we have to give any ping command or something. It will.
Yeah, if any broadcast traffic.
Okay.
Because your STP is not going to wait for you to create the broadcast and create the loop.
Okay.
It will already prevent the loop. Okay.
And that would be wasted, right?
Yeah, that would be wasted. Means ultimately your topology will be working without this link.
Okay.
Clear?
Full basis, like completely.
No, if any of the link goes down, let's say, for example, let's say I delete any of the link. If I delete this link, now you'll see it will come up.
But
Still,
again, we have to wait for 50 seconds.
yeah, it is going to take some time. Okay. And again, as soon as this comes up, every time a link is added or removed, you'll see same thing again. Okay, this is clear.
It will not remember, but it will again do the.
Yeah, the calculation will be again done. This is clear to everyone?
Every 2 or 3 seconds, they will keep.
Yeah, the repeating. Any doubt in the STP? No? Online people?
No, Ajay.
Okay. Next, we have ether channel concept. So this is used to prevent the redundancy. So we'll discuss this one tomorrow. Okay. Because today, practical and theory both will be not possible. So we'll do it tomorrow. So any doubts? All right, then see you guys tomorrow. Have a great day.